Hi, everyone, and welcome. Thank you for joining us today. I am Chandel Hoover, APA Director of Science Special Projects and Implementation. Today's program is part of an APA Science Training series that is focused on the integration of new tools and techniques to support cutting-edge psychological research. We hope you will visit our Science Training Session webpage to check out the rest of the training sessions in the series. All sessions are being recorded, and everyone who registers will receive a link to the recording about 2 weeks after the live stream. We also invite you to subscribe to Science Spotlight, your source for the most relevant news, information, funding, and opportunities for psychological scientists. Before we get started with today's session, I want to share a few quick announcements. First, thanks to those of you who submitted questions for today's program when you registered. You can also ask a question as the program is taking place in real time. There's a Q&A feature on the dashboard. Please enter your questions there. We'll be monitoring those questions throughout the program. Again, this program is being recorded, so once it ends, everyone who registered will receive an email with the link to the recording. You should receive that email in about 2 weeks. I'm pleased to introduce our speaker for today's training. Dr. Blankson is a professor of psychology at Spelman College. Her substantive research interests include the organization and development of cognitive abilities as it relates to personality, parenting, and schooling. Her quantitative interests include measurement invariance and structural equation modeling. We are thrilled to host this session with you today and appreciate Dr. Blankson's time.
All right, thank you all for joining today for this session on factor analysis. I'm really excited to present about the topic to you all. What I will start off by saying is that it's a session primarily an introduction to factor analysis. The primary focus will be on exploratory factor analysis. There are many aspects of factor analysis that could be discussed in more detail. So I'll start off by saying what this session will not cover. These include factor scores, confirmatory factor analyses, how to conduct confirmatory factor analyses, Bayesian analyses, factor analyses with categorical variables. A whole session could be devoted to these topics. Additionally, there are several issues that researchers must consider before conducting factor analyses. What I've listed here are a few issues, but these are important topics to consider. Reliability of your variables and your data. Sample size is important to consider. There are various recommendations for sample sizes for factor analyses ranging from, say, 500 participants, 1,000 participants, and so on and so forth. Researchers should also consider how they plan to deal with outliers, how they plan to deal with missing data before they start their factor analyses. Now, because of more recently, individuals are pre-registering studies, that means that researchers have the opportunity to iron out a lot of these details and have plans for what you'll do to handle these issues well in advance of conducting the factor analyses. Additionally, factor analysis does make the assumption that data are linearly related, so that's something important to take note of, and matrix algebra. Having a good understanding of matrix algebra can help you know more about what's going on behind the scenes of a factor analysis. In today's session, I'll go through examples using R on how to conduct factor analyses, and you'll see that sometimes it's like one line of code. But there's a lot that goes on behind the scenes dealing with the multiplication and other types of things of the matrices. So having that understanding can improve your understanding of what factor analysis is and what's going on behind the scenes when you're running the analyses, and can help you with interpreting the results as well. All right, so all the resources can be found in this Posit Cloud account, and the APA organizers are also going to post a link for how to access the files in PDF format. So near the end of, or middle to end of the session, I will do like a tutorial on how to do factor analyses, and the POSIT Cloud account has the documents that are needed. But if you're not working with me live, then you can refer to the PDF of the slides as well. All right, so let's get into it. Suppose they have a set of variables and you're interested in understanding the underlying structure of it. Factor analyses allow us to summarize the patterns of correlations. So for example, here you have a correlation matrix, you see ones in a diagonal, and variables 1 and 2 are strongly correlated, variables 3 and 4 are correlated, and the two pairs of variables appear to be somewhat correlated with each other. Factor analysis can help us to reduce this set of data. Here it's 4 variables, but in most instances is more than 4. To reduce them into fewer variables, keep in mind that when I'm speaking and the example that I present today, I refer to things as variables. I use the term variable, but these can be items, such as items on a Likert type of scale, or these could be scores. So maybe there are scores on various tests and the researcher wants to do certain tests lumped together. Those are some of the things that factor analyses can be used to understand. There are different types of analyses that can be conducted to understand the underlying structure of data. These include principal components analysis, exploratory factor analysis, and confirmatory factor analysis. Confirmatory factor analysis is also referred to as restricted modeling analyses, and that's because researchers have in mind a certain structure of the data and they fit their data to that specific structure. Often, this uses structural equation modeling framework. Principal components analysis is another method of reducing data. And then exploratory factor analysis is what the focus will be on for this session. There are several situations in which researchers might choose to conduct factor analyses, such as with test development, theory development, construct validation. And I've listed these separately, but they're not necessarily mutually exclusive, because in development tests, it can inform theory, and theories inform test development, and all of that is part of that construct validation process as well. Related to this is the fact that exploratory factor analysis, principal components analysis, and confirmatory factor analyses, all of these could potentially be used in one study. And by one study, I mean like one researcher conducting a study, maybe developing a test, and they've written a set of 50 to 100 items and want to see what underlying constructs, what do these different items measure? Maybe some of the items measure anxiety, others measure depression, and others measure like openness to experience, for example. Analyses can be, the researcher might start off with exploratory factor analyses and then conduct confirmatory factor analyses. It's important to note, however, that a large sample size would be needed to conduct all of these analyses in one study. So the researcher could select a random sample, random portion of the data and do the exploratory factor analyses. And based on those results, do a confirmatory factor analysis on another random portion of the data. But ideally, replication is important, right? Once exploratory factor analyses, replication is important to confirm the structure of the data. So exploratory factor analysis can be like a starting point for researchers. So before discussing principal components analysis and exploratory factor analysis, I'll go over some terms. Now, there is a question that's directly connected to this that's been put in the chat, and someone has asked that sometimes individuals in the literature use principal components analysis and exploratory factor analysis. It seems that they're using it synonymously in the literature, but perhaps as I talk more about the differences between these, you can look in the literature, read those articles again and see, are they using them synonymously or not? Because they have different, they serve different purposes. All right, so observed correlation matrix, reproduced correlation matrix, residual correlation matrix, loadings, commonality, uniquenesses, and eigenvalues. It's important to understand the terms because when you do the analyses and you run your analyses in whatever software you use, you'll get a lot of output. And understanding the terms will help with understanding the output and how to approach the output, because there can be a lot of information that's there. So before getting into the differences between principal components analysis and exploratory factor analysis, we'll talk about these terms. The observed correlation matrix is a matrix of the correlations between the variables or the items, similar to the correlation matrix that I showed on previous slide. The reproduced correlation matrix, what comes out of the factor analysis. So the observed correlation matrix, or some version of the observed correlation matrix, goes into the factor analysis. The reproduce is what comes out of it. Residual correlation matrix then is what's left over, like the difference between the observed and the reproduced correlation matrix. Factor loadings can be thought of in a similar way to regression coefficients, and loadings generally represent the relation between a variable and the factor. Then you have this concept of commonality. The commonality is the proportion of a variable's variance that can be accounted for by the factors. So you're trying to explain the relation between several different variables. You do your factor analysis, you come up with a set of factors. Commonality tells you how much of the variable's variance is explained by the factors that you've obtained. Uniqueness then is what's left over. So if you think about the variable's variance being 100% of the variable's variance being explained, or we translate that to a value of 1, right? So 1 minus commonality is a uniqueness. And then final term for now is eigenvalue. Commonality explains variances across a variable, for a variable. Eigenvalue represents the variances for the variance for a factor. How much variance does a factor represent or account for? All right. And so now let's look at a visualization, a structural model of the difference between principal components analysis and exploratory factor analysis. In the figure, the circle represents a latent component, latent variable, latent factor, something that's not measured, a latent variable. The rectangle represents observed variables or items, and the arrows represent the direction of effects. What you see here is that for principal components analysis, the arrow goes from the variable to the factor, indicating that the variable, not factor, sorry, component. The variable goes, the arrow goes from the variable to the component, indicating that the variables define the component. In contrast, what we see with factor analysis is that the arrow goes from the factor to the variable, indicating that the factor predicts the variables. The values, when you run your factor analysis, the values represented by the arrows would be the factor loadings or the component loadings. Here are some additional differences between principal components analysis and exploratory factor analysis, and can help researchers decide on whether they should conduct a principal components analysis or exploratory factor analysis. That's a question that was asked, is why, when would one choose to do the factor analysis versus a principal components analysis? With principal components analysis, you're analyzing variance, which consists of both the common variance across the variables and the unique variance. Principal components analysis is a procedure that tries to account for all the variance for each variable. And in contrast, exploratory factor analysis analyzes the covariance or the commonality among the variables. The procedure attempts to account for only what's common across the different variables. Principal components analysis will produce components. In contrast, factor analysis produces factors. With the components, it's an attempt to identify what's the best weighted linear combination of all of the variables. Whereas with factor analysis, the factor is also a linear combination, but it accounts for that common variance across the variables. Principal components analysis starts off with the observed correlation matrix that has the ones in the diagonal and tries to give you back that exact observed correlation matrix. In contrast, exploratory factor analysis will try to produce an approximation to that observed correlation matrix. And for principal components analysis, usually there's no underlying theory about which variables go with each other or how the variables will go together. But in contrast with exploratory factor analysis, there's usually some underlying theory or hypothesis when researchers are examining those results. So in the example in R, I'll provide code for how to do a principal components analysis, as well as exploratory factor analysis. So let's talk a little bit more about exploratory factor analysis. So starting off with some more terms and steps when conducting an exploratory factor analysis. Now, these are general steps to follow, but it's exploratory, right? And it's called exploratory for a reason. So you might go back and forth between these steps. You might extract some factors, rotate, interpret, go back, extract, and so on, trying to make sense out of the data. With factor extraction, we're starting off with figuring out, what should go in the diagonal element. The differences between different factor extraction methods are really, you might think of it as, how the diagonal elements are filled in for the start of the factor extraction. So factor extraction, when you think about extraction, like pulling out, like your teeth are extracted or whatever, they're pulled out. So the factors are pulled out of the data. And what goes into the analysis is going to be some kind of matrix, but the diagonal elements will not necessarily be one, which is in contrast to principal components analysis, where the diagonal elements are ones. So the factors are extracted in a manner to try to approximate that observed correlation matrix. And then instead of ones in that diagonal, squared multiple correlations might be put in the diagonal, the largest correlation, reliabilities, or even some extraction methods start off with ones in the diagonal and then go from there. So you can see that there are different methods for factor extraction. Principal components is a method for factor extraction. And what that means is that the correlation matrix that is for how the factors are extracted starts off with ones in the diagonal. But then, the matrices are multiplied in different ways that make it different from the principal components analysis, because with factor analysis, it's trying to understand or explain the common variance, right? So generally, what distinguishes the different methods, because there are quite a few, is what goes in the diagonal. So, some of you attending this session right now might be wondering, well, how do I make a decision about what extraction method to use? The important thing to understand is that the more variables you have in your analysis, the less it kind of matters what goes in the diagonal, because there'll be more off diagonal elements that are being explained, right? And so through iteration, the analysis process, there's a search made for loadings that are going to give the best approximation to the observed correlation matrix. And as I mentioned, when you have more variables, you'll have more off diagonal elements, and the different extraction, there won't be that much difference in the different extraction methods. Additionally, as the commonalities, as the extent to which the variables are common, as that approaches one, then there are virtually no differences between the extraction methods as well as principal components analysis. So the closer these values are to one, anyway, there are a few differences between the extraction methods. So how do you decide on the number of factors that are in the data? There are different methods for determining the number of factors. And this kind of goes hand in hand with interpreting the factors. One of the methods for determining how many factors there are among a set of items is the root 1 criterion. And what this criterion is about examining the eigenvalues, and the eigenvalues are how much variance represent how much variance is explained by each factor. And with the root 1 criterion is saying, extract as many factors as there are eigenvalues over 1. So in this example here, we have, let's say these are the first 4 eigenvalues. One is 3.13, second is 1.40, 0.99, and 0.79. According to the root 1 criterion, if these were the eigenvalues that we got out of a factor analysis, then it would suggest that there are 2 factors. However, the root 1 criterion does not necessarily work as well as the parallel analysis and the scree test. So I should mention that John Horn was my graduate school advisor. He did develop the parallel analysis. I'm not biased though. But parallel analysis and the scree test are the most commonly used, and the research seems to support using these approaches to help identify the number of factors that there are. In this plot that you see here, the blue line represents, it's a plot of the eigenvalues and can be used for the scree test. And then the red line is the parallel analysis part of the plot. For the scree plot, it's, as I mentioned, it's a plot of the eigenvalues, right, against the factors. And it involves subjectivity, when trying to use it, because basically researchers look at this, you see here, this blue line, and try to determine where it starts to level off. And that's the scree test. So as a researcher, you would create this scree plot, this plot of the eigenvalues, and then you would look to see where it starts to level off, and you would conclude, I might conclude that, oh, this looks like it's leveling off around 3 factors. Parallel analysis is based on comparing the eigenvalues that are obtained from a set of random numbers with the eigenvalues that are obtained for the correlation matrix. So you, with scree plots, they're a little bit more subjective. With the parallel analysis, is the red lines represent the eigenvalues that are from the simulated, the random data, and you look to see how many eigenvalues in the observed data fall above the eigenvalues from the random data. So looking at this plot, the parallel analysis and interpretation of the parallel analysis, you would look at the blue line to see how many of those values fall above that red line. And what we see here is that there are 3 eigenvalues that fall above that red line. So the conclusion from the parallel analysis would be, in this case, that, oh, there are about 3 factors in these data. Sometimes you'll so as we saw for these this example, like the Root 1 criterion suggested there are 2 factors. Parallel analysis suggests there are 3 factors. Scree test suggests that there are 3 factors. Okay, what are you supposed to do as a researcher, right? Well, you could extract 2 factors and look to see how the variables are going together and whether it's an interpretable solution. You could extract the 3 factors and, interpret that solution. You could even extract 4 factors, see what that looks like. You're not stuck to saying, oh, the parallel analysis said 3 factors, so I'm going to extract 3 factors and that's it. Because there, as we'll talk about, there's much more to trying to understand and explain and interpret the factors beyond saying, oh, there are 3 factors. That, are the factors meaningful? If you have 3 factors and one of them is completely, if let's say first factor has all positive values and the second factor also has positive values and the third factor has all negative values, and it looks like it's a flip of the first factor, well, then that third factor might not make sense. So these techniques are like guides to help a researcher determine how many factors that there are. Then once you extract factors, factor rotation can also be used to make solutions more interpretable. Factor rotations are linear transformations of matrices. The factor loading matrix is rotated according to some criteria. The specific criteria are what differentiate the different rotation methods. Ideally, the rotations are conducted in a way to arrive at a solution that has a small number of non-zero loadings. And there are 2 overall types of rotation that researchers can choose to use: orthogonal rotations and then oblique rotations. Orthogonal means that the factors are not related to each other. So the factors are extracted. You say you have 2 factors and these 2 factors are not correlated. So with orthogonal rotation, it will rotate the factors in a way to make the to distinguish the factors from each other, and the factors are not allowed to correlate. So when the math behind it is trying to figure out these loadings, it's not allowing the factors to be related to each other. In this kind of instance, the researcher is assuming that factors are independent from one another. All orthogonal rotations are pretty much mathematically equivalent to each other, as well as to the initial solution before it was rotated. The purpose of the rotation is really kind of like to clean things up, to help you with understanding how the items or variables are going together. Two orthogonal methods are Varimax and Quartimax. With Varimax rotation, it's essentially trying to make high loadings higher and low loadings lower within a factor. So let's say there are 3 factors. The Varimax rotation is going to try to, within each factor, have several high loadings, but other low loadings. And then factor 2 would have different variables that have the high loadings and different variables that have the low loadings. In contrast, Quartimax rotation attempts to make the high loadings higher and low loadings lower within the variables. So Varimax rotation tries to simplify the factor. Quartimax attempts to simplify the variables in simple terms. Of course, there's much more behind, the math behind what all of these are doing, but we're not going into all of the math behind these techniques. Oblique rotations allow factors to correlate, and they might be more realistic than orthogonal rotations because factors might be related with each other conceptually. Some of these methods include Oblimin and Promax, and there are common methods that are used in factor rotation. With Promax rotation, you start off with an orthogonal solution and then rotate it again in a way that allows the factors to be correlated with each other. Oblimin rotation minimizes the extent to which variables are loading on a lot of factors. But if you have an oblique solution and the factors are related to each other, it might be more challenging to interpret those results because to the extent that the factors are related to each other, the variables might load on more factors. So depending on the level of correlation between the factors, it might make oblique solutions a little bit more difficult to interpret, but oblique solutions might be the best approach to use conceptually because let's say you're developing a new measure of anxiety and depression. Well, anxiety and depression are related to each other, right? So if you were to say, well, I'm going to do a factor rotation that keeps these constructs orthogonal, unrelated to each other. Maybe that's the purpose of your new measure, right? You want to make a measure where you're identifying these constructs, but they're not related with each other. But maybe you're developing a measure and you understand that conceptually these variables are related, these constructs are related to each other. So then you might decide that for this measure that you're developing, then an oblique solution makes the most sense. All right, so various matrices are produced from the factor analysis. And dependent on the software that you use, the software has certain default settings and will display certain matrices, and maybe not all the matrices. Maybe you have to request each of the different matrices using coding or other techniques. But there are some matrices that are produced, even if they might be behind the scenes, and you have to call out for them. These include, for the orthogonal rotation, there's a factor matrix that is produced. The factor matrix has the factor loadings, and factor loadings represent that correlation between the observed variable and the factors. With oblique rotations, because you're allowing the factors to be related to each other, then you will get other matrices beyond that loading matrix. there's the pattern matrix, which is a matrix that's of the loadings, but whereas the factor matrix, the loadings represent correlations between the factors and the variables. With the pattern matrix, because the factors are correlated with each other, they're not really correlations, right? The loadings no longer represent correlations, but they're like regression, like coefficients where so the loadings represent the unique amount, the unique relation between a factor and the observed variable. The structure matrix is that matrix that represents the correlation between the variable and the factor. Sometimes that's referred to as a standardized load-in matrix. So depending on the software that you use, you might get different labels for these matrices. So it's important to know what these, with the software that you're using, it's important to know how they're referring to these matrices so that you're interpreting them accurately. And then the factor correlation matrix is the matrix of the correlations among the different factors that are extracted. I've said a lot of words. Let's look at an example factor analysis result. This here's an example from a rotated solution. In the first three columns, you see that there were three factors that were extracted and then rotated. And the values in the columns represent the factor loadings. In the commonality column, we see that the commonality represents the shared variance with other variables, and the uniqueness is what's left over. So we see for this WM variable, commonality is 0.62, uniqueness is 0.38, and you add it together, you get 1, right? Indicate 100% of the variance accounted for. You can see in this result that there are, for factor 1, there are some variables that have higher loadings and other variables that have lower loadings on each of the different factors. And then you can see that some of the variables have more commonality than other variables. So in this example here, the WM variable has the highest commonality value versus this inhib variable that has a commonality of 0.28. And so these results are indicating this inhib variable still has some differences, something that distinguishes it from the other variables. It has a higher uniqueness. And then complexity represents the extent to which items are loading on one or more factors. So the closer the value is to 1, the less complex the variable. But if you only do an analysis and you extract one factor, then your complexity values are going to be 1. So complexity should not be used to interpret how many factors there are. What it's showing you is, of the factors that you've extracted, about how many are the variables loading on. So that is what complexity represents. Okay, there was a question in the Q&A about what high complexity means, and so I think I just answered that. And then somebody asked, what does a negative factor loading mean? And that's a great question. When interpreting factor solutions, it's important to have the items and the meaning of the items right along with it. When John and I, John Horn, when we conducted factor analyses years ago in my graduate program, we would print out a bunch of factor solutions and have the items there next to it. And here's the solution, and look at it together. Because when thinking about how to interpret factor analyses, this goes right into criteria for decision making, right? It's important to think about, theory. Does this make theoretical sense for a loading to be negative? Maybe the researcher wrote a bunch of items and reverse scored those items before doing the factor analysis. Let's say it's I've been using depression and anxiety, so I'll use that. Let's say they're depression items. And so some of the items were worded in a direction of high scores indicate high depression. Other items were worded in a direction of low scores indicate high depression. So those low scored items might have been reversed in advance of the factor analysis. But let's say you do the factor analysis and you're getting negative loadings even for the items that you had initially reverse scored. Well, that could mean that the item isn't working the way that you thought it would, that you thought it would work. Or if you didn't reverse score in advance, then the negative loading could be, oh, you should reverse score these items. So a negative loading is not necessarily interpretable by itself, like, oh, this is what a negative loading means. But you have to think about, what do these items mean? And then what did I do in creating this correlation matrix that went into the analysis before doing the analysis? And that will help with interpretation. And then there are other criteria that can be used as well. I'm going to pause for a second and take a look at some of these questions and see, because they're connected with some of the things that were just discussed. So somebody asked about, in the context of scale development, are commonality and uniqueness relevant for deciding on items to retain or remove from a scale? And it could. So if you're developing a scale, and so in this slide here, where we see this INHIB has more uniqueness than others, maybe more items need to be written to assess that construct in a future study, or maybe it's not going with the other items in a way that you were expecting them to. So maybe it's a reason to revise and create a scale and have more items to assess that aspect of the construct that you're trying to assess, or remove the item remove the item from the scale. Another question: after conducting the EFA and some items have been dropped due to poor loadings, is it important to redo the analysis, excluding the items that were dropped during the first analysis? And then what's the implication of excluding the items? So you can redo those analyses, excluding the items. You can do confirmatory factor analyses on like what the result was. But one of the things that I have said before, and I'll keep saying, is that ideally a new sample would be used, or let's say a different random half of that sample. So a researcher shouldn't really do an exploratory factor analysis and say, I've found these factors and there, and this is what it is for the, it's really seeing the extent to which these factors will be replicable. All right, so let's talk a little bit more about these decision-making things. Whether the solutions are theoretically and empirically sound is important. Thurstone's simple structure is the idea that researchers try to identify factor solutions where you have factors with a lot of higher loadings and some lower loadings, and variables that are not they're not complex. So variables that are not loading on multiple factors. there are some decision-making criteria, such as using 0.3 loadings above 0.3. Researchers can say if a factor loads above 0.3, then if a variable loads above 0.3 on a factor, then it will be considered to load on the factor. 0.3 is sometimes used as a cutoff. Sometimes researchers might use 0.4 or 0.5. Sometimes that cutoff is decided based on the solution that's obtained. So if using 0.5 would put a variable on a factor, and let's say a variable loads on one factor 0.5 and another factor 0.3, then a researcher might use the 0.5 cutoff and say, oh, this variable goes on the factor where it loads 0.5 and not on this factor that loads 0.3. As you see, there's a lot of subjectivity in the decision-making process. And that's why that replicability is really important, because of the subjectivity that goes into these decisions that we make when we're trying to explain or interpret the factor solutions. And then there are the different types of factors. So the common factors are the ones where you have variables loading on the factors. A singlet would be a factor where only one variable loads on the factor. And so the researcher has to think, well, maybe you didn't write enough items to measure that aspect of the construct. And so either write more items, go back, collect more data, and then, have a stronger potential of measuring that factor, or remove that item from the analyses. Null factors could can result where the factor has variables that have very low loadings on them. Then I've talked already about that, the unipolar and bipolar factors. So you can have a factor that has items that are all in the same direction, and factors that have items that load in opposite directions. And as I mentioned before, when there's opposite directions, it might be that the item doesn't need to be reverse scored, or if it was, then it's not working the same way that it was, that you think it was working. Okay, so there's a question here about the different types of rotation. Is there no correlation between factors? Or are you assuming that there's no correlation between constructs that you're exploring? That's a good question, because when you do that extraction, you are making that assumption that there's no correlation, but it might not be a realistic assumption. So that's where the researcher has to think, is this type of analysis realistic for the concepts that I'm trying to understand? All right, so and replicability, naming of factors. Naming of factors doesn't make it what it is. And that's kind of a problem that we have in the literature, is that researchers will, do a factor analysis and they come up with a whole new name versus what's been used in the literature. It seems like, oh, it's a new thing, but it might not be. Or maybe they use an old name that represented something else, and individuals will think that that factor represents this old thing when it doesn't. It represents a new thing. So it's really important to think about how you're naming the factors. If it's a construct that's similar to what's been in the field and there is some theoretical reason to keep that same name, then keep that same name. But if there's good reason to give it a different name, then give it a different name. But whatever the name of the factor is doesn't make make it what it is. That's important to keep in mind. All right, so let's go back to this example that we have and can apply some of the criteria that I've just discussed in thinking about interpreting the results. Looking at factor 1, we see that there are several very larger loadings and then several smaller loadings. The WM variable has the largest loading. So when we're thinking about how to understand this factor, we might use whatever that WM item is stating to help guide us in naming that factor. And it might be considered, this variable might be considered a marker variable if it's only loading on that one factor and is loading the highest on that one factor. So we have these three variables on that first factor. Factor 2, we can apply, the same criteria. We see that we have several higher loadings. Now, if we were using the 0.3 cutoff, it would work for this analysis. We have several large loadings and then several smaller loadings. And the marker variable in this case might be vocab. And then factor 3, several larger loadings and then smaller loadings that are salient on this factor. And the marker might be number series, but there might not be that large of a difference between these loadings here, the 0.64 and 0.58. All right, so applying the criteria leads us to having 3 factors with 3 variables each. And then now if we layer on the meaning of these variables, we can then put names onto our factors. So we might label, if you're in the cognitive field, you might label factor 1 as executive function. Factor 2, you might call crystallized intelligence measured by vocabulary, comprehension, and general information. And factor 3, fluid intelligence measured by number series, matrix reasoning, and concept formation. But not all solutions are that pretty. Maybe most solutions are not that pretty. So here's a different example, and you see here some of the variables load on more than one factor, and decisions that are made will depend on the purpose of the analysis. So a decision in this case might be to remove the number series variable from the models because it doesn't load higher than 0.3 if 0.3 is the rule of thumb that you're using. It doesn't load 0.3 on any of the factors, and then it loads on multiple factors. And you can see that this item complexity is 2.85 close to 3, loading on the 3 factors that were extracted. With the matrix reasoning test, on the other hand, it's loaded on 2 factors, has a complexity of 2. A decision for that one might be to remove it as well from the analysis. All right, so as you can see, there are some strengths of factor analysis because it can help us to understand how our variables are going together. But there's a challenge because there are a lot of solutions, in fact, an infinite number of solutions that you can compute. And so how does a researcher make sense of all of this? Thinking about what makes sense psychologically, what makes sense psychometrically, when you look at the items and then how they're going on the factors, does it make sense theoretically? If the items were supposed to be reverse scored or not, does the direction of the loadings make sense? And so all of these things are some of the challenges with factor analysis. And I mentioned about the naming of factors. Spurious factors can also result. So if you have variables that are not reliable when you are conduct your factor analyses, what you get out of it might not make sense. Is that whole idea of garbage in, garbage out. You get out of a factor analysis what you put into it. And factor analysis is not going to save bad data or a poorly designed research study. And so it's important, or even poorly written items, right? So if you're constructing a new test and you have items that are double-barreled, so you have and statements in an item, or items that are not written well, the factor analysis isn't going to save that. And in fact, the factor analysis might show that, oh, these items are not written very well. So all of those things that I mentioned that are important to do before factor analysis is actually important to do before the factor analysis, because as you can see, there's already a lot that goes into even trying to interpret the results. And to the extent that you don't have a good research design, don't have well-written items or reliable variables that are included, that can make the interpretation even more challenging. Replication, confirmatory factor analysis. researchers might choose to use factor scores in subsequent analyses, but my recommendation would be to get a little bit more support for the factors that were obtained through the exploratory factor analysis before using it in further investigations, whether it's using the separate random portion of the sample or a completely new sample in the analyses. On the slides, I also have a few additional resources to learn much more about factor analyses as well. So now I'm going to shift over to the example using R, and as mentioned before, all of these resources can be found in the POSIT Cloud account shown there. And the example uses Quarto through POSIT Cloud. And so if you want to follow along, you can, but it's, a bit recorded on the video. You can follow along later. And so I am going to now shift and share my screen for the POSIT Cloud account. And if my contact information is shown here, it's on the slides, and it's also in the POSIT Cloud documents that you'll see. All right, so shift into the example in how to conduct factor analyses. And I have a lot here. We'll see how much time there is, but I have in the account, there is the tutorial where you can go through and, like type things on your own to see, to actually do the exercise for yourself. But then that's the one that's labeled tutorial. But then there's also the file that has everything, all of the codes typed in that you can use as a reference. Now, those of you, I don't know how many of you are familiar with R or not, but this is one resource for conducting factor analyses. Some might use SPSS or other statistical software packages for conducting the analyses. With R, you can write scripts. The Quarto allows you to create other kinds of documents like HTML or PDF or even PowerPoint. So it uses Quarto, and you can see how to create different documents. I'll talk about some data management, the factor analysis examples. There's some principal components analysis examples, and visualization. Might not get to the visualization. Might not get to the visualization. Now, I see some individuals are not familiar with R or POSIT Cloud. These are, R is open source. It is, there's a basic functionality, but then for other types of analyses and visualizations and so on, anyone can contribute to R and write different functions to allow people to do pretty much anything these days, whether it's creating maps or pictures or so on. And it can be used for statistical analyses, similar to, some might be familiar with SPSS or SAS or M+. These are other software that can be used. And so, all right, let's get into it. You see up here at the top, you can put different information. So, put your name or the date there, and then echo equals true when we are, go through the exercise and we do what's called rendering the document. It will create a HTML document. So if you're working along and you have this, actually the tutorial version of it, and you click this blue button to render, hopefully it'll work. When things happen live, they don't always work. But wonderful. You should see a HTML document that's created. And it has the code in there, as well as whatever other text that you put in there. So that's where echo equals true, warning equals false. So echo equals true says when you print these, when you create this document, put the code there. And you can change it to say echo equals false if you want to. All right, so let's actually get into these things. Packages. Packages allow you to do much more behind the scenes than, not behind the scenes, much more than the basic R. The psych package is a common package to use for different statistical analyses, including factor analysis, and is the package where the factor analysis function I use in these examples come from the psych package. Additional packages that you might need, dependent on whether you're working in the cloud or whether you're working on R on your local computer, include Markdown, knitr, and then the nice thing about working in this type of document is that you can label each of your code chunks, and it helps you to navigate in your code better, I think, than some other options for working with data. I also like R because it allows for reproducibility. So you can see here, I shared the R, the Posit Cloud space with you all, and it has the data there and the code there. You can share it with others and they can do the same. And when I teach my students, they can, share theirs with me and I can look things over. All you need is the code and the data to, to be able to reproduce things. So the package that we're going to add here is we're going to install .packages, and we're going to bring in the psych package and then library psych. So installing a package means that you are bringing it into the R session, but when you do library psych, that's when the functions become available for the different types of analyses. So we'll need the psych package, and then might also need, again, this depends on how you're working. So I'm putting all these packages here. GPA rotation is a package that might be needed for one of the analyses there. And when you write your code chunk, you can run each individual code chunk. And I'll say, I don't know if you see the pop-up box on my end, but I'm not going to restart my R session because I was working on it in advance and it has some things already in there. But for you all, you probably wouldn't get that pop-up box to say that you need to restart it. Also, if you're working on the cloud account that I sent for you, you might see at the top left, it says temporary copy, and it's like in red. That means it's a temporary copy. So to the right of it, you'll see it says save a permanent copy. So if you are working, or whenever you do work on this, do save that permanent copy. Then what you have and what you do on there is yours, and it's in your own workspace, and it's not temporary. Temporary means temporary. All right, so variables that are in the data set that you see here, this is the data set Intro FA 2024 April. General information, these variables were created for a sample of 500, and they are on a scale of mean of 100, standard deviation of 30. The data, you see the data here, but it's not recognized by R as a data set that's usable. Instead, you have to read in your data somehow, bring in your data. This is different from SPSS, where you open the data set and then you're pointing and clicking, or you open the data set and write the syntax like the data are there. Here, the data are in a folder, but R doesn't know that it's there and how to use it. You have to tell R what to do. So we'll do that by bringing in the data, and we're going to label it. Imagine that you had a data set on your computer and you had it saved as my data. That's what we're doing. We're going to call it my data and use the read.csv function to bring in the data. And in this case, you it's called intro FA 2024 _ April. R.csv. R is case sensitive. You have to put the case as is, or it'll say that something's not found. So I'm putting in the data. I'm going to bring it in the data, and I'll run the current code chunk. And as you can see, it brought in the data, 500 observations with 9 variables. Next, descriptive statistics. These are, you know, a quick example of how to do factor analysis, but all the background stuff, I cannot stress that enough. Has to be done before doing the factor analyses. So descriptive statistics, basic descriptives and correlations can be important to do in looking at your skewness and kurtosis, the distribution of the data, whether you have, whether data were entered accurately. All of those things are important to do. So before doing these descriptives, one thing to note is that R will sometimes print in scientific notation. And if you want to get rid of the scientific notation, you can put this code in, option SciPen equals 999, and it'll print out the decimals for you. But the code for describing the data is describe, and that comes from the Scikit package. Describe and my data. So it's going to compute means, standard deviations, skewness, kurtosis, and so on for each of the variables. And you do, as a researcher, should examine these statistics to see if it makes sense to even use these data for your analyses. You can also examine the correlations between your variables using the core.test function. And the core.test expects, you know, to compute a correlation among a set of variables. And it expects all the variables to be numeric, so not categorical variables in there. And in this case, it produces, and I ran the current chunk, and it produced the correlation matrix there, and we can see that the variables are related to each other. Some correlations are much stronger than other correlations are. And there's a question about whether data need to be normally distributed to be used in factor analysis. Factor analysis doesn't have as many assumptions of the data as other types of analyses, but you know, that linearity of the linearity of the that their data are linearly related is important for the analyses. All right. Okay, so there's a question about acceptable levels of skewness and kurtosis. So there's some standards that skewness between -1.1 through 0 to +1 indicates normal skewness, and anything outside of it is either skewed right or skewed left. Kurtosis, -1.5 through 0 to 2.0, but there are some standard like rules of thumb to use. And it's always important as a researcher to make a decision about what rules of thumb you are, like what kind of person are you? What kind of researcher are you? And what rules of thumb are you going to use? Are you going to be more conservative or more liberal in the rules of thumb? Similar to when we get down to looking at the factor analysis results, these results will provide goodness of fit indices. If you're familiar with structural equation modeling, goodness of fit indices have been developed, and there's some standards that, for example, with the root mean square error approximation, like 0.05 might be a standard, or 0.08 might be a standard. So as a researcher, you should make that decision on how you will interpret and what rules of thumb you'll use. And probably a good idea to be consistent to the extent possible in different studies that you do. But of course, statistics, just like with other research, we learn more about these statistical analyses that we're doing and these criteria that we're using over the years. And so you know, use the latest knowledge to help you to make those decisions about what's acceptable values or ranges or not. All right, so now the factor analysis. So factor analysis is that multivariate method. You have multiple variables trying to understand how are these variables going together. And we talked about how you could do the parallel analysis and the scree plot. So let's, the code fa.parallel is the function for the parallel analysis. And we're doing a parallel analysis for the data set that we called my data. And we want to do a parallel analysis on the factor analysis. You could do a parallel analysis for principal components as well. It'll produce those output. So this slide should be familiar. If you have a question, feel free to put it in the Q&A. But let me run it again and see. All right, that's prettier. All right, so the parallel analysis, and we looked at the example when I was presenting earlier, and the scree plot. So you look at the scree plot and you see where does it tend to level off, and here it might be around 3 factors. Parallel analysis, the smaller dots are the assimilated data, and then the larger dash line or the thicker dash line is resample data, but examining how many eigenvalues are above the eigenvalues for the random data. Here it seems like there are 3 factors. All right. We can also, the number of eigenvalues that there are also can be used. So you can request eigenvalues independently of the factor analysis, since eigenvalues are a method for determining how many factors there are. With the eigenvalue analysis, it's conducted on a correlation matrix. So you would use the eigenfunction and say that I want to do the eigenvalue on a correlation of my data, the correlation matrix of the variables in the data set called my data. And we run that. It does the eigen decomposition. So you can, pay attention to these where it says $ values. Those are the eigenvalues, 3.13, 1.40. So if you're using the root 1 criteria, you might say that there are 2 eigenvalues above 1, but this value of 0.988, if we were to round to 2 decimal places, that would be 1. So you might say that there are 2 or 3 factors according to this root 1 criterion. All right, so factor models. This first example here that we'll do is using the default settings. It uses minimum residual procedure for extracting the factors, and that's an ordinary least squares procedure for factor extraction. There are other factoring options available in the psych package, but with this, we are going to, and so this is the part where you're like, oh, how do I do a factor analysis? And I had mentioned before, like 1 line of code and you'll do your factor analysis, but it's the understanding of how to interpret and all the things to do beforehand that's really important, because here we are about to do a factor analysis. So we're doing a factor analysis, going to store it into an object, store the results so that we can print different parts of the results later. So the function for it is actually FA, which is from the psych package. And we're saying do a factor analysis for the data set that's called my data. And we run that, and it's conducted the factor analysis for us. It doesn't print anything in the results yet because we said, do the factor analysis, put everything in an object called, we called it EXFA, example factor analysis. And that's, here it is up here. So now we can request certain things out of that. If you click on, we can click on it and see what that looks like. So it has information, but we can request to see that information in a way that's a little bit prettier. So we're going to type in, from the example factor analysis object that we created, show me the values, which are like saying, show me the eigenvalues. And it prints out the eigenvalues for you from the factor extraction. This is with no rotation and min-res, minimum residual extraction. You can see the eigenvalue is different from when we looked at the other set of eigenvalues, and that's because these are eigenvalues associated with that first factor, or pulling out just one factor. We can also then view the factor results by typing in XFA and running that, and you'll see what the results of the factor analysis are. And as I mentioned, you'll get a whole lot of information. And without having that background understanding of that information, it can be more challenging to interpret what these things mean. You'll get the factor loadings. All right, so here we extracted one factor. We get this column MR1, and that is the first factor. And in the column are the loadings on that first factor. Now it's labeled MR1 because it used the minimum residual extraction, and there are other extraction methods, maximum likelihood, and so on and so forth. So the label might be ML, or if it's a principal components analysis that you do, you'll see PC, but those are the loadings, and you'll have as many columns as there are factors or components that you extract. H2 represents the commonalities, which is that shared variance. The U2 are the uniquenesses. Com is not commonality, it's complexity. And as you can see here, because only one factor was extracted, the complexity is 1. But again, don't confuse this with how many factors are underlying these set of variables, because we only asked for one factor. It's saying these variables load on the one factor. Then you see SS loadings, which is the sum of squared loadings, which is equal to that eigenvalue that we got when we printed that eigenvalue. See that here, the 2.46. That's what the sum of squared loadings is. So if you take these variables, the 0.55, you square it and you add them up, you'll get the 2.46, 0.55 squared plus 0.55 squared, and so on. That's where that 2.46 comes from. And that's what an eigenvalue is. So if you're like, oh, different, new terms, eigenvalue, but that's how it's computed. It's also referred to as the sum of squared loadings. We get the proportion of variance accounted for, explained by the factor. And then the mean item complexity, if we have one factor, that mean item complexity is going to be 1. And then we also get different fit statistics for these analyses. Now, if you do the analyses in SPSS or other software, you might not get the fit statistics. Generally, you get fit statistics when you do the confirmatory factor analyses, and it's saying how well does this structure that you're imposing on the data fit. These fit statistics are saying how well does one factor model fit with the data. And we can see root mean square of residuals. We get the root mean square of residuals in this case, and the Tucker-Lewis index, root mean square error of approximation. These are all different types of fit indices. And as I was talking about before, there are different rules of thumb for interpreting these values. So RMSEA, whether you use the 0.05 or 0.08 or 0.10 rule of thumb for RMSEA, it's the 1.24 is above that, suggesting that these data might measure more than one factor. And then you get other information, the correlation of the regression scores with the factor, the multiple R squared. So you're familiar with the multiple R squared concept. This 0.79 is the square of the 0.89. Minimum correlation of possible factor scores. So you get different information out of the factor analysis to help you to interpret what you're getting. With this solution, my conclusion would be that probably these data don't fit that, don't measure one factor. The results seem to suggest that they measure 3 factors. So let's extract 3 factors. And we're going to store it in an object, call it xfa_3. And it's the same function, fa, and then the data set is called my data. Now we're going to tell it extract. We're going to extract using the psych package, n factors is equal to 3. We're going to extract 3 factors. And rotate using Varimax rotation. And Varimax rotation is an orthogonal rotation. So saying pull out 3 factors and then rotate it in a way where the factors are not related to each other. And now I want to view the factors. So I'm going to just type in XFA and run it again. So it prints out the solution for the 3-factor model. Which I'm not seeing. Oh, because I asked to print out the XFA, which is a 1-factor model. So I have to say exactly what I want, which is the 3-factor model. All right, there we go. This is the 3. Now you can see how it has the 3 different factors, the ordering, why this called 3 and this called 2 is not of too much relevance, but it has the 3 factors, commonality and uniquenesses as well. And you can see here, because the factors are not correlated with each other, but you get a little bit more detail. So you get the cumulative variance because you have multiple factors, and it's telling you how much do they relate, how much variance is explained across all the factors. You get differences in the mean item complexity, and you still get the variable various, correlation with the factor and so on. In this example here, I selected the Varimax rotation as an example of computing an analysis where the factors are not related with each other. And as an example to all for if you wanted to do a Varimax rotation, if you wanted to do an oblique rotation, so I'll call it 3P for Promax, then we would conduct the analysis, and it's still the same FA function, and we're still using the same data set. In this case, I still want 3 factors. And now I want the rotation method to be Promax. So that's the difference between the Varimax rotation and the Promax rotation in terms of the syntax. And then I'm going to print out the results. So now I've run the Promax rotation. You can see that it's the pattern matrix and it's labeled that way here. You have the loadings, looks a little bit different than the Varimax loadings. And then you have difference from the Verimax result is you have the factor correlations, right? So because of time, there isn't much time to go through live with the principal components analysis and the visualizations, but you do have all of that in, so the tutorial, you can, work on the tutorial, type it in on your own, but it's here for you all there, where how you do the principal components analysis. Instead of FA, it's going to be PCA and Verimax rotation. And then some of you might be interested in, what do the data look like? What does a factor analysis solution look like? So you can create matrix, a scatter plot matrix, or 3D scatter plots that plot the variables on each factor. I think if I were to render this, rendering it live, let's see, so that we can see what all of the, there we go. Wonderful. So when we when you go through and you can type it in all on your own and then work through it, you can see the principal components analysis. And I would recommend printing these out. We can do a lot on computers, or you have a large screen, right, and look at things side by side. If you're doing your own analyses, so you can see what the differences between these results are. For these variables, they're cognitive variables, you would expect them to be related. So a Promax rotation might make the most sense for these analyses. And then the visualizations, here you have a scatter plot matrix of the Verimax solution. Verimax, they're not related to each other. Here are the 3D matrix of the factor loadings. Verimax rotation, the factors are extracted to be orthogonal to each other. And then, but the Promax, they're related to each other. So you can see that visualization where the Promax, the variables are kind of a little bit more closer together, lumped together, than the Verimax rotation where they're separated out. So there's one way you can take a look at the factors. I know that was a lot of information, but my contact information is here. There's some additional resources as well. William Ravel wrote this slide package with, and colleagues as well. And then more about Quarto if you want to learn more about Quarto. So at this time, I'm going to pass it off back to Shandell.
Dr. Blankson, thank you so much for this fabulous presentation and all the thoughtful lecture materials. We appreciate everyone being here and the great questions that you asked. Just a reminder that we did record today's session. In about 2 weeks, we will send a link to the recording, a transcript, and the lecture materials to everyone. In about mid to late May, we will update our APA Science webpage with links to recordings for all the sessions that we've had. We have one more science training session, April 30th, on eye tracking. We hope you can join that. Go to apa.org/science, look for science trainings. If anyone is interested in NIH grants, there's a brand new framework, peer review framework for that. So we hope you can join us for an essential science conversation about that. Also, go to apa.org/science to learn more about that. When we close here today, you should receive a 1-minute survey to complete. We would love your feedback. The topics that we have in this series came directly from that survey, so please let us know what you think. You can also email us at science@apa.org with recommendations. Last, we hope you subscribe to Science Spotlight. It's a free newsletter. You can get access to news, information, funding opportunities. So we hope that you'll join that. And again, much thanks to everyone for being here, and certainly to Dr. Blankson. We hope everyone has a wonderful day. Thanks so much.